Hi, I'm James Dials, and this is my lecture on how to use backtracking to solve a Sudoku puzzle. Sudoku is a number placement puzzle that is logic-based. Sudoku is normally played on a 9x9 grid. There are 9 3x3 subgrids. The objective is to fill the 9x9 grid with digits 1 through 9, such that each of these 9 digits appear once in each row, column, and each 3x3 subgrid only one time. Here's an example of a Sudoku puzzle and its solution. So we'll be using backtracking, which is the same as lecture 23 from our class. About 5 steps. The first step is to form a state space tree for the problem. Then decide on the promising function. Perform a depth first search on the tree. And during the depth first search, evaluate if continuing to the child node is promising. A solution at each node. If there is, continue to the child node. If not, prune the non-promising branch. Then we find all of our solutions as we reach the leaves on the state space tree. So to apply this to Sudoku, we can use this tree. Each possible number is tried for each empty space on the Sudoku puzzle, and at each level until each possible number has been exhausted or pruned. Just to explain the tree a little bit more in notation, the circled X stands for the root node. The empty circles are candidates. Dark outlined circles are leaf candidates. Red circles are failed candidates. Green circles are found solutions. And the tree shows possible paths as well as backtrack paths and solution paths. Here you can apply that. The second step is to decide on the promising function. And for Sudoku, this is done by selecting the next empty spot or cell, placing the first possible number in that empty cell, then checking the constraints of the Sudoku problem, i.e. 1 through 9, once in each column, row, and subgrid. If a node is non-promising or it breaks the constraints, we can backtrack. This is done repeatedly until a final solution for the entire puzzle is found. During the depth first search, we need to evaluate if continuing to the child node is promising at a solution each node. If yes, continue to the child nodes. If no, prune the non-promising branch, which is using that promising function that we just explained. So I use some Python code for backtracking. So I'll just go through that. So as we explained before, the first step is to find the next empty cell. So we'll do that in a for loop, and then we'll check that, we'll place our first value starting at 1 in that empty cell, and we'll check that that value has not already been used on that row. If it has, we can backtrack. So this is where the first example of backtracking starts. So we can just eliminate checking the column and subgrid for all of these possibilities that obviously aren't going to be in the solution. So the next step, once we've checked that row and found a possible solution, we'll check that this value is not already in the column. Then we'll identify which subgrid we are in, as the code states squares, which is the same thing as a subgrid. We'll check to find out which subgrid we are in. That way we can check the constraint that the value that we're using is not in that subgrid, which is this next piece of code. Checking that that value is not in that 3x3 square. So we'll continue to do this until we find all of the solutions, and then that'll give us our solution to our Sudoku puzzle. So there are multiple algorithms for solving a Sudoku puzzle. Obviously, we can go about this with brute force. It's obviously the worst possible thing we can do. The efficiency is pretty horrible, which I'll go over in the next slide. One of the most popular algorithms is dancing link. It can solve that 9x9 grid in seconds. Once we start to raise the dimensions, it starts to get a lot slower. This is actually an MP hard problem, and I'm not going to go too much into it, but I suggest researching that a little bit because it's pretty cool. But then we have the algorithm X, which is written by Donald Knuth, which is just an application of dancing link. So I'll refer to algorithm X, which is basically dancing link. So the efficiency analysis, we have brute force, which is m times n cubed. As you can see, that's pretty bad. The algorithm X, or dancing link, makes it a little bit more efficient, n by n cubed, which is better, but this is just an NP hard problem, so there isn't a polynomial solution for this, at least not yet. Alright, any questions? Just comment and I'll answer them. These are the resources that I used.